Okay, so calculate the following sums. So, we have, for natural log, okay. So this one is like, U1 is natural log 2, and then U2 is 2 natural log 2, and then U3 is 3 natural log 2, up until 10 natural log 2. So if we have U1 is natural log 2, and then how we get from U1 to U2 is by adding natural log 2, and we have 10 terms because it goes from 1 to 10. So we've got, sum of 10 terms, and this is an arithmetic, and we're going to have n over 2, 2u1 plus n minus 1 times d. So this is 5 natural log 4 plus natural log, actually, we'll just leave it as 2 squared, plus natural log 2 to the 9th. This is addition, so we can multiply 2 squared times 2 to the 9th, which is 2 to the 11th. So this should be 55 natural log 2. So for B, this one's different because we're multiplying. So natural log 2 is U1, but we're multiplying by natural log 2. That's our R. So we have, again, the sum of 10 terms, but now we're in geometric. So we've got U1, R to the 10 minus 1 over R minus 1. And for C, we're doing that sum to infinities of the same thing. So we've got U1 over 1 minus R. So for 59, we've got the sum from 1 to 50 of that. Okay, so this is going to be, so if you write the first couple, this is natural log 2 when R is 1, natural log 2 squared, which is this, natural log 2 cubed. So this is going to be the same thing as was in the previous one. So U1 is natural log 2, and the D, to get from here to here, you're adding a natural log 2. And N is going to be 50. So we've got the sum of 50 terms. It's arithmetic, 50 over 2, 2u1 plus n minus 1 times d. And this one, 25, natural log 2 squared plus natural log 2 to the 49 is going to be 25. And we can multiply natural log 2 squared times 2 to the 49. We add exponents. So 51 times 25 natural log 2. So 60, find an expression for the sum of the first 35 terms of the series, giving your answer in the form that. Okay, so 2 natural log x. And then the second one is 2 natural log x minus natural log y. And then it's 2 natural log x minus 2 natural log y. Okay, so we're going down. Okay, so D, we're subtracting natural log y every time. Okay, U1 is 2 natural log x. or natural log x squared, and we want the 35 terms. So this is arithmetic. 35 over 2. 2 u1, I'm going to write it like that, plus n minus 1 times d. Okay, so now 35 over 2 natural log x to the 4th minus natural log y to the 34. And 35 over 2 natural log x to the 4th over y to the 34th. And then we will have that 35 over 2 goes to like this, 35 over 2. So that's going to be natural log x to the 70th, because it's 35 times 4 over 2, over y to the 17 times 35, whatever that is, because it's going to be 35 times 34 over 2, which is 35 times 17. All right, the function f is defined for x greater than 2 by that. Express f at x in that form. So for a, we have, we can get this together by multiplying, because we're adding, and then dividing by this. And they want it in that form. So when we factor the bottom, that's x plus 2, x minus 2. Those will cancel, so final answer is x over x plus 2. B, so if that's y equals, we want x equals natural log y over y plus 2. And we can write this exponentially, so e to the x equals y over y plus 2. Cross multiply, e to the xy plus 2e to the x equals y. Y is on one side. And factor it out. So that's 1 minus e to the x. So our inverse function is going to be 2e to the x over 1 minus e to the x. And the, if we wanted the domain, we want to see when the denominator is equal to 0. So if we have 1 equals e to the x, x can't be 0, which is the range of this one. And y greater than 2 is the range of the inverse. All right, for 62, we've got, write down the value of f at a. So if we have f at a is log base a of a, and this is equal to 1, because a to the 1 equals a. So for double I, f at 1 is log base a of 1, and that's equal to 0, because a to 0 is 1. And triple I, f of a to the 4th is log base a of a to the 4, which is equal to 4, because a to the 4th equals a to the 4th. For B, the diagram below shows part of the graph of f. On the same diagram, sketch f inverse. So if we've got 0, 1, 1, 0, we've got 0, 1 here. And the asymptote is at x equals 0. So the asymptote here is at y equals 0, and it's going to go like this. So for 63, we've got that function. Given that the inverse at 1 is 8, find k. So this is y. This is y, this is x. So we're going to have 1 equals k log base 2 of 8. Well, log base 2 of 8 is 3 because 2 cubed is 8. So k is 1/3. Now we want the inverse at 2/3. So we've got 2/3 equals 1/3 log base 2 of x. So multiplying by 3, we're going to have 2. And then writing it exponentially, we're going to have x equals 4. All right, f at x is that, g at x is that. Express g in the form that. Okay. So g at x, we need to separate. So we're going to have natural log 5 plus natural log x cubed, which I'm going to put that out there, and that's that. So a is 5. Now, because this is f at x. The graph of g is the transformation of f. Give a full geometric description of the transformation. I think it's just up natural log 5, because this is f at x, and then this is just a number outside the function, so it's a vertical shift up natural log 5. All right, f at x is that. Show that the inverse is that. So we've got to do x equals log base 3 of square root of y. So if we write this exponentially, we've got 3 to the x equals, and I'll do y to the 1/2, and square both sides. So we're going to have 3 to the 2x is the inverse. B, write down the range for the inverse. So that's the domain of the original. So that's y greater than 0. And let g be that. Find the value of that. Okay. So we have the inverse at g is 3 to the 2 log base 3 of x. And then we need to substitute 2 in there. So that's 3 to the log base 3 of 4. And this is just equal to 4. Because if we have y equals 3 log 3 of 4, and we write this logarithmically, we have log, the base is 3 of y equals log base 3 of 4. So right there you can see y is 4. All right, let f at x equal that. X greater than -2, g is that, x greater than 0. Write down the x-intercept of f, so we need to set y to 0. So writing this exponentially, we've got e to the 0, which is 1, equals x plus 2, so x is -1. For b, I, we want f at -1.99, so that's natural log -1.999 plus 2. And in the calculator, that's -6.91. For double I, we want g at 4, so that's e to the 4 minus 4, 0, which is 1. For C, find the coordinates of the points of intersection of the graphs of f and g. This you need to graph, which is right there. So we've got, those two. And that, with the hand over it, is 0.006784. But if you look at the domain for the black function, it's only good for x greater than 0. And if you look for the blue function, that's only good for x greater than -2, which, yeah, it's all this because the asymptote should be here at -2. So yeah, this one doesn't count basically because it has to be the intersection of the two, like their domains, which is x greater than 0. All right, f at x and g are that. Write down the inverse of f. So we have x equals e to the y, natural log both sides, and or write it exponentially, logarithmically. So this is the inverse. All right, b, inverse of that. Write it exponentially, e to the x equals 1 plus 2y, sorry. So e to the x minus 1 over 2 is the inverse. And that's actually g. All right, c, find g of f at x. So we've got, that's natural log 1 plus 2e to the x. And double I is f of g, so we've got e to the natural log 1 plus 2x. And by the same thing we did up there, when we equal this to y, you can see, like if we write this logarithmically, we'll have natural log, because the base is e, of y equals the natural log of 1 plus 2x. So we get that y is 1 plus 2x. Okay, so that is going to be f of g at x. Okay, now d, find f of g, the inverse of that. So just to recall, if we have f that maps x onto g, all right, so this is going to be f at x. I guess that's written improperly. So rather, this is x, this is the function, so this is going to be f at x, and then our next function is g, and this is g at x. So if we want the inverse of that, we have to go backwards. So this, we need to inverse g first. Hold on, let me write this better, because this is actually g of f at x. So, like I said, if we go backwards, we can undo g first, which is going to give us f at x, and then we need to do the inverse of f. So that means that if we want the inverse of f of g, we need to do the inverse of g like this. So that is going to be, hold on, let me get a different, this, that's the inverse into g inverse. So we're going to have e to the natural log x minus 1 over 2, and this kind of cancels out for all those reasons above. So we've got x minus 1 over 2.